For part 2 of this lecture, we're going to talk about probability tables. Let's revisit our example of health insurance. So again, suppose you're a public health researcher, but now you're interested not only in health insurance, but poverty as well. You want to look at these two variables. Again, you obtain data from the American Community Survey, and your question is, you want to know how likely is it that Americans are to be uninsured and poor, economically impoverished. So you want to look at the probability of these two events occurring at the same time. Here's our data set again. Just to remind you, we have 343 people, so we have 343 rows, and then we have all these great variables. The variables that we're really going to focus on are health insurance and whether or not the respondent is living in poverty or not. So one way to think about looking at these two events of being poor and not having health insurance existing together is to create a probability table. We've actually seen this before. So a table of unconditional proportions, you can think of it as a table of probabilities. A probability table is used to answer the kinds of questions that we're talking about right now. We want to know how likely is it that an American is to be poor and not have health insurance. So let's think about these as two random phenomenon, right? Previously, we were just looking at one random phenomenon, having health insurance. And remember, when we talk about a random phenomenon, we're talking about just some process, some thing in the world that involves some level of uncertainty. So let's talk about looking at two random phenomenon, and we're going to call one event A and one event B. Before we talked about the probability of event A equals some probability, but when we talk about A and B occurring together, we want to talk about the probability of A and B. So we assign a probability of these two events occurring together. This leads to the discussion of joint versus disjoint probabilities. Two events, A and B, are joint if they occur at the same time. The idea is that if they can occur at the same time, if they can both happen at once, these two events are joint or mutually inclusive. We can talk about two events being disjoint or mutually exclusive if the occurrence of one is incompatible with the occurrence of the other. If they can't happen at the same time, two events, A and B, are disjoint. The joint probability of disjoint events is 0, meaning if you have event A and event B, the probability of A and B occurring together, it's impossible. It's 0. In that case, we would say that two events, they're disjoint. So here's an example of joint versus disjoint events. So disjoint events, they're just mutually exclusive. They can't happen at the same time. So if you look at a sample space of flipping a fair coin, you have the probability of getting heads or the probability of getting tails up for that one coin flip. These are two disjoint events. They're mutually exclusive. When you flip a coin, you can't get heads and tails. It's either heads up or tails up in that one coin flip. Another example is drawing a card from a deck and having that card be both an ace and a king. Okay, that's impossible. A standard deck of cards, you can't have these two events occurring at the same time when you draw one random card. Another example of a disjoint or mutually exclusive event is having a birth year of 1985 as well as 1990. You just have that one birth year. You have that one year. You can't be born in 2 years unless you're a time traveler. Examples of joint or mutually inclusive events are many, and the idea behind joint events, they can happen at the same time. The occurrence of one is compatible with the occurrence of another. So you could flip a coin that lands heads up, and you could also draw an ace from a deck of cards. You could do that simultaneously. It'd be a little bit weird, but you could do that. These are two events that are joint. You could have a birth year of 1985, and you could also draw a card that is a king. Again, these events can happen at the same time. Now, when we have a Venn diagram, recall a Venn diagram is just a way of partitioning a sample space to really understand what's going on. We can really visualize joint and disjoint probabilities. So here I've given the joint probabilities and disjoint probabilities for A and B. So in this case, the probability of A is given by a blue circle, and the probability of B is given by a yellow circle. If those two circles overlap in a Venn diagram, then those are joint probabilities, meaning the probability of event A and the probability of event B, there's a joint probability. They can occur at the same time. If they don't overlap, there is no joint probability. They are disjoint. So if probability A and B are joint, they overlap, and we can talk about the probability of A and B equaling some value other than 0. If they don't overlap, the probability of A and B is in fact 0. It's impossible. And so we talk about those events being disjoint. So here's sort of a contrived example. Suppose event A is being born into a wealthy family, and B equals working as an investment bank as an adult. Well, that can happen at the same time. Okay, you can have those two events occur in a person's lifetime. A disjoint example would be suppose A is being born into a wealthy family and B is being born into a poor family. Now, you're either born into a wealthy family or you're not. So these would be disjoint events. So the probability of A and the probability of B would be 0. So you can see that a Venn diagram is useful for looking at understanding the difference between joint and disjoint probabilities. Now, when we work with joint probabilities, okay, the key point here is that for probability of A and the probability of B, we can kind of divide it out together. So we can express the probability of A as equal to that joint probability, the probability of A and B, plus the probability of only A, meaning the probability of A and not B. So here's an example. Suppose the probability of A and B is 0.2, and the probability of only A is 0.5. Then you can just add those up together to find the probability of A. You can see that when you have a Venn diagram, it can make working with joint probabilities a little bit easier. Because all really this is saying is that if you have a joint probability, then if you just look at that part that is unrelated to B, the probability of only A, and you add that joint probability with the probability of only A, you get the overall probability of event A. So let's look at an example of health insurance and poverty. Again, you are a public health researcher, and this is your research question. You have this set of data, and earlier we said, how likely is it that Americans are to be uninsured? And we found, well, the probability is 0.12. But now we want to say, we have two events. We have this event of being uninsured, and we have this event of being economically poor. And we want to say, how likely, how probable is it to be uninsured and economically impoverished? To put it another way, we want to find the probability of not just A, but we want to find the probability of A and B. We want to see what's the probability of these two events occurring together. So the idea of answering this question, how we do it, is we just create a probability table, which is just a table of unconditional proportions. And then we want to examine that joint probability based on that table of proportions. So here's our table of counts. This is a contingency table, and these are the actual frequencies. So the total sample is 343 respondents. So we have 343 people in our data set. And you can see that we have marginal totals and we have cell totals. What we want to do is we want to convert this contingency table into a probability table. So all we do is we just want to make sure we divide each cell by 343. But before we do that, we should keep in mind that we're treating these different levels for each categorical variable as a different sample space. So we're in essence saying the possible outcomes for being poor, it's non-poor and poor. We're saying, okay, these are mutually exclusive and collectively exhaustive possible outcomes. That's the sample space. And then for the health insurance example, for that variable, these two levels of no and yes, you have no health insurance or you do have health insurance, we're treating those as the sample space for this process of having health insurance. And so the idea is that these two events, that's the sample space, and that sample space is, again, exclusive and exhaustive. You either have health insurance or you don't, and that's the full range of possible outcomes. So we want to just double check to make sure that we've expressed the sample space in a way that is valid, right? Recall sample spaces have to be exhaustive and exclusive. Then the next step is, when we've kind of thought about these different categorical variables as in terms of the sample space, we want to create this table of probabilities. It's just a table of unconditional proportions. So you just divide each cell by 343, the total sample size, and we get this table of proportions, which we want to treat as probabilities, as empirically derived probabilities. Now, the one key point about this is just a table of unconditional proportions. When we view a table of unconditional proportions as probabilities, it's useful to look at the marginal probabilities, right? So the probability overall of having health insurance is 0.88. And the probability of not having health insurance, the complement of having health insurance, is 0.12. Now, this is a valid sample space, so 0.12 plus 0.88, that equals 1 within rounding error. We can also view the categories of non-poor and poor. That's the sample space for this process of being economically impoverished. That sample space also equals 1. It's a valid sample space. And then we can think of these cells. These are giving the joint probabilities. These are giving the probabilities of any particular events. So for example, this cell, it gives us the probability of having health insurance and being not poor. So the idea is that that is a joint probability. It's equivalent to the probability of A and B, where A is having health insurance and B is being not poor. These are the probability of these two events occurring at the same time. These four joint probabilities, that's a sample space, and that must equal 1 as well. Within rounding error, when you actually collect this set of data, there will be some rounding error, but these four mutually exclusive and exhaustive outcomes will also equal 1 within rounding error. So in our analysis, our key question is, how likely is it that Americans are to be uninsured and economically impoverished? How likely is that event A and B to occur at the same time? Well, we can say that that probability is 0.09. To put it another way, there's about a 10% chance, give or take, of somebody being poor and not having any health insurance. With that, we've really kind of concluded our discussion in terms of joint probabilities. Next, we're going to explore other ways of investigating how to work with joint probabilities.